In this paper, we present TANDEM, a method to learn efficient tactile exploration policy jointly with decision making. Humans are experts at using touch sensing. For example, we can efficiently explore and search inside a bag and then retrieve a particular object. We, as roboticists, would like to ask the question, with a robotic manipulator and a tactile sensor, can we complete similar tasks in the absolute absence of vision? However, tactile sensors can be powerful but can also be challenging to use. It is fundamentally an active sensing modality, and touch sensors provide local and sparse information through each contact. As a result, the guidance for tactile exploration is extremely important. Without a smart guidance, the sensor can only blindly scan on a surface or continuously make repetitive contacts. This introduces high cost and burden on the robotic manipulators. In this work, we focus on the guidance for tactile exploration. The question we want to answer is, how can we learn efficient tactile exploration guidance in conjunction with task-related decision-making? The task we choose to study is tactile object recognition, where one object must be identified out of a set of known objects based only on touch feedback. The goal of our method is to correctly recognize the object with as few actions as possible. In our test setup, we mount a tactile finger on a robot arm, and the object is placed roughly in the center of a workspace. The object rotation along its z-axis is unknown and random. Our object is from a set of 3D printed random-shaped polygons. Without visual feedback, these polygons can be challenging to identify even for humans. In order to learn an exploration policy with decision-making, we identify three key components in our proposed architecture. The explorer generates an action for the robot to take in order to collect more data. In our implementation, the explorer consists of a PPO agent trained via deep reinforcement learning. The discriminator predicts the identity of the object along with the confidence value. This is a supervised learning problem, implemented using a convolutional neural network. Finally, in addition to the explorer and discriminator, the encoder converts the sequence of local and sparse tactile signals into a global representation. In a tactile object recognition task, the tactile sensor interacts with the target object in the environment and outputs local and sparse sensor data. In our task, we use the binary collision signals. The encoder keeps a sequence of binary signals and rearranges them into an occupancy grid. The discriminator takes in the occupancy grid and attempts to identify the object along with a confidence estimate. If the confidence is higher than the predefined threshold, the exploration is terminated and the final prediction is produced. Otherwise, the explorer reads the representation and generates the next move. Despite that we have separate and distinct exploration and decision-making components, their training are highly interleaved. To begin with, both the discriminator and the explorer are initialized randomly. We first collect an initial dataset of occupancy grids and their corresponding labels using random explorer. The discriminator is then trained with this dataset for a number of epochs. We then fix the discriminator, use it to provide episode termination signals to the trained explorer for a number of steps. The explorer is trained with RL and is rewarded when the discriminator becomes certain and terminates the episode. During the training of the explorer, a new batch of labeled occupancy grids are collected, and then the process repeats until convergence. In this co-training process, the discriminator affects episode termination, and the explorer affects partial observability of the labeled training data. Every time one component gets improved, the other component adapts to the distributional shift. As a result, the discriminator and the explorer co-evolve, gradually pushing the other to improve and eventually converge. Binary collision signals are easy to simulate, which facilitates a large amount of training steps in simulation. As a result, our method is trained entirely in simulation and then zero-shot transferred onto real robot. Our learned exploration policy is able to accurately predict the object identity with very few actions. It learns behavior similar to edge following, but can take shortcuts, utilize non-collision pixels, and also is very robust to sensor noise. On our tactile finger, sensor noise occurs when a contact is reported on a non-collision location, as highlighted in the right circle. We then demonstrate these behaviors using real-world videos. The finger approaches the object along the diagonal. We visualize the occupancy grid representation and the predicted distribution over 10 objects. Different from edge following, our finger can take shortcuts when appropriate, and it quickly converges to the correct identity of this object. In this example, it only takes 40 actions to recognize this object. With such little information, even humans cannot tell the identity correctly. This example demonstrates the finger's behavior to utilize the non-collision pixels. As you can see, towards the end, it improves its confidence by exploring non-collision areas and then makes a correct prediction at a collision-free location. In this example, we demonstrate the noise robustness behavior. As the finger approaches the object, a fake contact is detected due to sensor noise. But our learning exploration policy continues exploring until a true contact happens. The finger initially recognizes it as object 7, but without high confidence. After the exploration around the corner, the prediction quickly converges to object 3. We further investigate the generalization ability of our policy to larger sensor noise than what the model is trained on in simulation. We present the number of actions, the effective action rate, which is the ratio of explored pixels to the total number of actions, and finally, the success rate. As you can see, despite trained only with 0.5% sensor noise, our method remains a high success rate and high exploration efficiency even with sensor noise up to 2.5%, while the performance of edge follower deteriorates more significantly. Thanks for watching.